Hi guys, can I get a sound check?
You're good.
You're good.
Start up. Okay. Sorry guys, I'm just trying to set up here. Okay, guys. By the way, I know a bunch of you guys, sorry, I've been like running my hair on fire here the last week or so. A bunch of you guys shot me emails. Just wanted to make sure that I had, can you guys hear me still okay?
Yeah, you're good.
Okay, great. So about like the regrades on the project, etc. So I'm sorry, I'm behind, and hopefully I'll catch up with all that stuff, you know, during the break. So so if like nothing good has happened, or I haven't caught up to what I told you guys I was gonna do by the time we get back from the break, please let me know. But I will catch up to all that, changing the grades and stuff, by till after the break. And then I think one of you guys, I don't know if you, I forgot who it was, I'm sorry, emailed me with a suggestion about how to set up the test, maybe make it available earlier on Tuesday. Does anybody mention that? Who's in the class right now? No? So I'll have to check my check my emails about that. So okay, so let's get going here. I think where we left it up was sort of the details of the transfer function for the inverter. So are you guys still hear me okay?
Yep.
Yeah, everything's fine.
Yeah, I think I'm using AirPods, and I think it keeps jumping between my Mac and the iPad. Sorry. So so if we were talking about the transfer function, which is like a DC response kind of thing, with a more realistic models for the MOS transistor. And today we're gonna talking about the transient response. Okay, that means delays, etc., through the device. So for example, if I was gonna jump in, remember we had basically, if we looked at a inverter, and we had a V in and a V out. So, you know, the VN would looks like, it wouldn't be, you know, if you look at a realistic transient, so this is time, and this is the voltage. So the horizontal axis is time, vertical axis is the voltage, and is the input. Doesn't quite look like, you know, our square wave, something like this. But this is what things would look like if there was another stage driving this Vn. So call that Vn prime or something. Okay, so Vn would look like, would have its own rise time. It would have some, you'll see why, you'll have some funky shapes here. You'll have fall time, some funky shapes here. And then our V out is an inverted version of the Vn. In this particular case, the supply voltage is 1 volt. So as Vn goes from 0 to 1 volt, the output drops from 1 volt to 0 and vice versa. And then you have these definitions of delay. You have the propagation delay. You have the rising propagation delay, which is the output rising. And the propagation delay is defined, if you guys remember, from the 50% point of the output to the 50% point of the input, or I should be really saying it the other way, from the 50% point of the input to the 50% point of the output. Okay, so this is our prop delay rising. The reason it's rising is because the output's rising. The prop delay falling is when the output is falling, and it's defined as the 50% point on the input to the 50% point on the output. Okay, so those are the propagation delays. Then the output has its own, so that's from, the prop delays are from here to here. Okay, so these are propagation delays from here. Propagation delay. Okay, and the rise and fall times are just here. Okay, so separately, the output itself takes some time to go from 1 to 0, and that's defined from the. This is, unfortunately, this is a different definition that was given before. And you'll see this difference. This is from 0.8 to 0.2 volts, so 80% to 20% drop. Before we talked about 90% to 10%, and we'll define that if you have a problem like that. And then the rise time is from the 20 to 80% here just on the output. So prop delay is between the input and the output of a single stage. Okay, so so anyway, I won't talk about the projects, but so there was some sort of confusions there. But the propagation delay for rise and fall are not guaranteed to be the same. So sometimes people talk about an average propagation delay. If you want to just give one number for the propagation delay, it's just the average value for the rise and fall times. Okay, so this is the main stuff you need to worry about for something like an inverter. Okay, now when you have other circuits, like let's say if you have a NAND gate, oops, how did I do that? See if you have a NAND gate. Okay, you'll have something also called the contamination delay. Okay, well, what does that mean? Okay, so let's say my draw time here, and I have my input is doing something. So let's say both. So let's say I have the same kind of thing. So I'm just going to plot the output. So this is going down, then it's going up. Okay, Now let's say this is the case. Now there's a bunch of different ways. There's only one way the input can go down, right? If so, output. There's only one way the output can go down. Output can only go down if both A and B are at VDD, right? Both these guys need to be on for the output to go low, okay? But there's more than one way for the output to go high, okay? So let's say this is a case where, because notice that if this one is low, or this A is low, or B is low, you can go high. Or if both of them are low, okay, you can go high. If both, so it could be that only one of these guys is on, okay, either this one, or it could be that both of them are on, okay? If only one of them, so let's say if both of them are on, right? So you're gonna have twice as much current pumping onto the output, charging that output up, than if only one of them is on. So if you have only A or only B is at ground, i.e. only one PMOS on, okay, you'll have a certain rise time. And if both of them are on, you actually get a faster, this is really poorly drawn here. So this is if both A and B are at 0, or both PMOS are on. Okay, so when you're looking at the rise time, it's actually possible, and each one of these will give you a different delay from the 50% transition point of the input to the output, because the delay of this red when only one PMOS is on is longer than the delay from the input to the output of the green when both of them are on. Okay, so the fastest change, so this is the fastest possible change on the output, is called contamination delay. Okay. And the longest delay is called the propagation delay. Propagation delay. Okay, so most of the time, people are only interested in propagation delay, because as you can imagine, that almost feels like, if you have you're stringing up a bunch of gates together, that's your longest delay, right? That's your worst case delay, you can think of it. So most of the time when you hear about delay in design, people are talking about propagation delay, or prop delay for short. You just constantly hear prop delay, prop delay, prop delay. But just sort of for the time being, keep the contamination delay in mind. It almost seems like sort of nonsensical to worry about something that's shorter than normal. But when we get to the section on clocking, flip-flops, timing, you'll see that you could sometimes having too fast of a transition under some circumstances across a gate could cause a problem, and we'll see how that works out. But anyway, just wanted for you guys to remember that there's this thing called contamination delay, because in certain circuits, in a lot of circuits, there is more than one way there's more than one delay from input to output. And it could be on the rising edge, it could be on the falling edge. Like for example, on a NOR gate, it will actually be on the falling edge, because on a NOR gate, you have the N's are in parallel and the P's are in series. So in a NOR gate, there's more than one way to pull the output down. Could be that one of these guys is on, or it could be that both of them are on. Okay, so just keep in mind that in anything other than an inverter, there's both a maximum delay from input to output, that's called prop delay, and then there's a minimum delay from input to output, and that's called the contamination delay. Okay, so anyway, this is what we're talking about when we're talking about a transient response. The times, the length of time required to get from input output or the output to transition. Okay, so again, going back to what we're doing here is we're trying to create some simple models for how these things work. So we created a simple model of using these load lines to figure out how how to look at the transition, DC transition, and therefore the noise margin, etc. So now we're gonna do a similar thing to try to come up with a simple model to get a better estimate for these delays, okay, or get an estimate for these delays. And these are the assumptions, simplified assumptions that we're gonna take, okay? First thing we're gonna do is we're gonna assume the input is a step function, okay? So what does that look like? Well, if this is VDD, we're gonna say, okay, the Vn is at some point at t equal to t0, the input is gonna go from 0 volts to VDD. Okay, so that's what the input's gonna do. And again, you guys are gonna remember, so it's a math concept. The way you would express that in an equation is you'd have a step function. Okay, that step function looks like it goes from, so if I was gonna draw u of t, it would go from, pick a better color. It would go from 0 to 1 at t equal to 0. So this is 1. Okay, so by saying times VDD. So if I say u of t minus t0, I'm shifting this over to some t0 over here. And by multiplying it by VDD, at this point, I'm going to have the number 1 multiplied by VDD. Okay, so I'm going to get, that's how I'm going to define Vn. Okay, and at time less than t0, okay, but below this, my input is low. So it means my output would have been high. So at t equal less than VDD, V out would be VDD. At t equal to less than t0, sorry. So it means if I draw my output, so this purple is my input. By the way, u of t has 0 rise time, means it's infinitely fast to go from 0 to 1. So we're not worrying about the input rise time in this. In other words, it's like a infinitely fast transition from 0 to VDD on the input. Real transition is going to look like it's going to have some rise time because something else is driving this and it'll slow it down. But So for the simplified expression, we're just assuming a perfectly flat, fast rise time, okay? So if I was gonna draw the output, it would be at VDD, so this is the output in green. So before, in this point, it'd be at VDD because it's an inverter. Okay, so if my input is zero, this guy's off, this guy's on, so it's making the output VDD. Okay, now what happens, the question is what happens here, right? We know the V out is gonna go from high VDD to ground somehow. The question is how. So how is this happening? Okay, so what happens is we're gonna get, we have a capacitor that's been charged to VDD, right? So here the capacitor's charge is VDD, and then it's gonna get drained by the current of this guy. Here, the NMOS current is discharging this capacitor and bringing the output low. So you could basically grossly say this is the IDSN over C subload. Okay, so basically the current through this guy is discharging the load. So as a function of time at each point, basically depending on how this current changes, this voltage changes that way, this way. Okay, now the complication again is that this transistor has various operating points. So let's now draw VDS versus IDSN. Okay, so I want to see what this looks like. Depending on what we said the input goes from 0 to 1, right? So the input is at VDD. So I only have one curve, okay, which is VGS is equal to VDD. That's the only curve I need to worry about. There's a bunch of other curves for, you know, as the input transitions from 0 to VDD, but for the simplified assumption, I'm not going to worry about that because I said my input goes infinitely fast from 0 to VDD. So I'm just going to have one curve of VGS to worry about. But the problem is, as the output changes, so as my output changes, my VDS is changing. So this is the drain. This is the source for this NMOS. So drain, source. And as this is discharging, as this point is going down, my VDS is shrinking. So my IDS changes as I'm going down here, my IDS is actually changing. And this is how it's changing. So less than t equal to 0, the IDS is just 0. The transistor is off. So this is the IDS for this guy, right? This guy's off, so there's no current going through it at time t is less than t0. When the V out is larger than VDD minus VT. Now remember, VGS is VDD. So this is the same as VDS, so V out, sorry. This is same as saying VDS of the N transistor is larger than VGS of the N minus VT. In other words, this is in saturation, when N is in saturation. So that's equal to beta over 2 VGS minus VT squared. Okay, and now also remember that this VGS is really VDD, because again, the gate became VDD immediately. So I'll actually use VDD, okay, for the current coming out when we're out here. When we're out here, the current is this, okay? When this is out here, this is the drain source voltage from the V out to ground. So this is a relatively high drain source voltage. And so I'm in saturation here. Now, as the output keeps dropping, at some point, I go into this linear mode. Again, this is the same as saying VDSN is less than VGSN minus VT. So this is, sorry, everything is turning up in the same color here. So this is linear. Okay, so this is beta VGS minus VT minus VDS over 2 times VDS. Okay. Okay, so that's the complication. We have sort of varying, sorry, this VDS should also be, because again, it went infinitely fast, so it should be VDD. And this VDS is V out, V out. So basically, the upshot is I go from off, this is an NMOS, on MOS. Let me just write it here. What color is good? Blue. So here, NMOS off. Here, roughly, we don't know exactly where NMOS is in saturation. And here we have NMOS in linear. Okay. Any questions about that? It's a really sort of complicated scenario in my mind. And it just comes from the fact that, again, this NMOS that we'd like to think of as a perfect switch isn't really a perfect switch. It's a transistor, it's a device that's doing this complicated sort of function with the voltage across it, but we're using it as a switch. So when you're looking at the actual timing in detail, it'll have somewhat of a strange timing. Okay. So, so again, why are we doing this? You know, we can just run this in simulation. We're trying to get sort of a rough idea of what these things look like. Okay, we're going to get an example, like a quick sort of the back of the envelope calculation, say, of what a delay through a particular size gate looks like. So we have a feel for it before we start simulating, etc. So, you know, what we do is we try to just simulate this as a first order RC. Okay, so what does that mean? We're gonna say, okay, this guy, let me just go back to this. So we have this fairly complicated set of currents, okay? And you have this change here. We're gonna put all of this stuff, okay? We're gonna print all of this stuff is like the key being is this is some R effective for the N. So R effective for N is some average equivalent resistance for the CMOS as it transitions, as its output transitions from VDD to ground. Okay, so we basically come up with some effective resistance, and then we can use that just as a simple RC network from then on, and come up with a real rough order of magnitude about the delay. Okay, why can we do that is because, well, let me see if I have a plot. The reason we can do that is because it actually gives a really good estimate. So this is a plot of, I think this is for a 65 nanometer process. So you see time here and voltage, okay? And it's comparing the simplified RC model, which is this dotted line, with SPICE, which is, I guess I don't know, it's level 49 or level 3 model, and just a simple Shockley model. And it turns out, that they're not like, so the main thing is really comparing this dotted line, which is this really simple RC model. So R effective. This R effective is important because that's the key. So what do we use for the R effective? But anyway, this says that if you pick the right R effective for your process, you actually get a pretty close approximation. You're not really sitting on top of your falling curve all the time. But if you're actually looking at, say, the propagation, so from, let's say you're looking at the 50% point to the 50% of your output, the dotted line and the black are actually, fairly close. And same if you're looking at, say, the 90 or 80% point to the 90 or 80% point here. So when you're looking at the totality of prop delay, or when you're looking at the totality of the fall time here, they're pretty close between your simulations. So it might be within, say, 10, 15% between a simulation and your hand calculation using this effective R. Now there's a couple of caveats here. Okay, one is I've assumed my input is rising infinitely fast. In reality, that's not going to be the case. So that's going to add a difference between simulation and this hand calculation. And the second thing is we need to figure out what this R effective is. We come up with a good R effective number. Okay, so that's what the point is here. Okay, so basically what we're doing is we are trying to come up with, we want to use SPICE, okay, itself, to come up with an R effective to use in our RC type estimations. Okay, so this is, I'm going to jump ahead to what we do to get it. Wait a minute. Is it here? Where'd it go? So I'll have to just try to. So this is what we do. So let's say I have, this is my VGS is equal to VDD, okay? Remember I said this is the only curve I'm gonna worry about because I'm assuming my input is infinitely fast. Everybody following me so far? You guys, any questions about what I'm doing or why?
No questions so far.
None, yeah.
Okay, great. So, okay, so I want to emulate, so let's see what happens. When I'm going from, for my prop delay, for my propagation delay, remember that, so my, sorry, I jump between these guys. So remember when I'm calculating prop delay, I'm saying my input is changing infinitely fast, and I want to go from there, the delay, to when my output goes to 50%. So out here, okay? So my input is changed infinitely fast. I'm immediately, my input is at VDD, and I want to see my output changing from the V out to VDD, from VDD to VDD over 2, okay? And because V out in the case of the NMOS is the same as VDS, if I look at it the same thing when I want to calculate my prop delay, assuming my VDS here is VDD, and I don't know, here is VDD over 2, okay? The main part of this curve that I'm interested in is my output has transitioned from here to here, here to here. Okay, that means that if I was gonna draw my, oops, I want to drive E, RC. So this is R effective, which I'm trying to calculate. Load. So basically this guy is going from VDD to VDD over 2. Okay, so I want to figure out what I can use for this R effective. Okay, so from having something like this. Okay, now if I just look at what's the quote unquote effective resistance at the highest point at VDD, I would say, okay, I'm about to do something really cheesy, guys, but this is the deal. Okay, if I was gonna have a resistor, that would be the equivalent. If this guy's just stayed at VDD, and what would be the equivalent resistance? It would be, as if I had a line here, it would be this R. So R at VDD is equal to, sorry, at V out is equal to VDD. By the way, you can immediately tell when I'm doing some hand waving because my voice tends to drop. So whenever you hear my voice dropping, it means I'm trying to get one by you guys. But I mean, this is how it's done, but it's really cheesy. Okay, so this is a resistance. Anybody have a problem with that? So this is, this is really 1 over R, right? The slope is 1 over R. So B is equal to IR, so I is equal to V over R. So the slope of this line would be my equivalent resistance when the output's at VDD. And the slope of this line is when, so this should be literally 1 over R. 1 over R at V out is equal to VDD over 2. Okay. And I'm going to pick the average of those. Okay, so this resistance, effective resistance, is equal to resistance, or I should say equivalent resistance at V out is equal to VDD plus equivalent resistance at V out is equal to VDD over 2 divided by 2. Okay, so just roughly something like, I don't know, like that. Okay, and I'm going to say, hey, I'm going to use this as an R value. The reason I'm going, because a resistor, when you plot a resistor, it has to go, it can't be like cantering off somewhere here, because that'd be a resistor with a voltage source. So if I'm just going to pretend like it's a resistor, it has to go through 0. So it has to be, this, or this. So that's why I end up with that effective resistance. Okay. Any questions about that? So long story short, you simulate or measure your IV curve of your transistor. So in fact, the nice thing about this, I don't know if I don't call it nice, but you aren't really, here to show you guys the problem or what we're trying to do. We said we're going to use, we wrote down the Shockley models, which we know aren't really accurate, right? Because of when you have smaller and smaller feature size transistors, these first order models aren't accurate. But if we're getting our average resistance value, no matter how cheesy our procedure is, if we're getting our average resistance value from the IV curve from our simulations, we're not using the Shockley model. We're using the actual whatever model the factory gave us to get this IV curve. So we've sort of eliminated the inaccuracies of the Shockley model, which is kind of good, I guess. Although we're still talking about a very simplified model. But again, we're replacing this current source with just an average resistance, okay? So this isn't good to predict the current or the actual voltage at any particular unit of time, at any particular time. But again, if you're looking at it in aggregate, so what happens when you're looking at prop delay, or rise fall delay, it's remarkably good, okay? And so let me point you guys to a useful chapter in the book. Oops. So I have the book here. Let's see. How do I do this better? Let's do it that way. Chapter 8. So there's a whole chapter on SPICE simulations. And there is a cool table here. Somewhere. Okay, so this is the table I'm looking for, I think. So, okay, so this table has helpfully given us or given some value for this equivalent resistance, okay, for different processes, some different processes here. Here's the process we've been using so far. So it's our TSMC 180 nanometer process. So if I look at the resistance here, it's in units of kilo ohm micron. And we'll see why it's got this funky resistance, this funky unit, okay? And if you look at it here and here, you'll see that or in our process. So if you did it, you basically ran the simulation, try to get this average resistance, which we might do as a project, if that's what we did in the previous semesters. You'll get this value of 2.69 kilo ohm microns for your equivalent resistance for the N. And you can do the same thing for the P. Again, we're down this column. So here and here. So you end up with 6.5 kilo ohm micron for the P. Now notice the equivalent resistance for the P is so 6.5 for the P and 2.7 for the N. I don't know, that's like maybe 2.5 times higher resistance for the P than it is for the N, which is kind of something we were expecting because we said the current through the P is, or the beta of a P or the mobility of P is 2 to 3 times less than the mobility current of an N. And we're calculating this resistance by the currents. So it makes sense that this resistance for the P ends up being 2 to 3 times higher than the resistance for the N. Okay. So let's get back to, oops, nope, wrong. Okay, so, okay, so now why was the resistance given in this? So this is, remember, R sub n was given in terms of, what was it, 2.7 kilo ohm micron, right? Something like that. Well, the reason for that is you run the simulation for a particular width of transistor. Remember, we don't want to change our L's, right? L is for a transistor is always minimum allowed. By process. Okay, but we can change our width. And as we change our width, so remember, so for example, in saturation, it's beta over 2 VGS minus VT squared. And so this is in saturation. This is Shockley model, but you guys get the idea. In linear, it's beta VGS minus VT minus VDS over 2 times VDS. So this beta is sort of this key thing. And remember that beta was mu Cox W over L. Okay, so that as you increase, if you keep L the same, the mobility is either mobility of electrons or the holes, so that's going to be the same. It's not going to change, or you don't have an option to change it. So you can't change this. You can't change the oxide capacitance. You don't want to increase L. You're always at the lowest L, so you're keeping the same. The one thing you can do is you can make your transistors wider. Okay, and the current through the transistor is linearly proportional to the width. So IDS is linearly proportional to the width of the transistor. Okay, so you calculate this for, say, your minimum width device or 1 micron wide device, whichever one you want to do. It's not going to matter much. And then from then on, if let's say you use a 10 micron device, okay, you divide this by 10 microns. So R sub n, if I use this, right, R sub n is 2.7 kilo ohm micron. This is, by the way, this is someplace, this is like everybody gets confused about this all the time. So So try to follow me if you can here. So for a 1 micron wide NMOS, R sub n is equal to 2.7 kilo ohm times micron divided by 1 micron. So that ends up being 2.7 kilo ohm. For a 10 micron wide NMOS, R sub n is equal to 2.7 kilo ohm micron divided by 10 micron. So that resistance, so let me use R sub n, sorry, R effective. Is 270 ohm. Okay, so if you make the transistor 10 times wider, resistance will go down by a factor of 10. Everybody good with that? Any questions? So just try to like remember that. This ratio, it'll immediately become probably, difficult. For some reason, it's like really hard to absorb when we take the next step. Okay, and same with the R sub P. Okay, R sub P was, I can't remember now, but say 6.51 or something kilo micron. So for a 1 micron wide P, this is all assuming that your length is minimum. So this is this is length is equal to 180 nanometer. So length. As soon as you use something else, you got to use a different R sub P, R sub n, okay? So for 1 micron wide, R effective P ends up being 6.51 kilo ohm times micron over 1 micron, or 6.5 kilo ohms, and R effective for a 10 micron P over 10 micron is 651 ohms. Okay, so any questions there? Okay, so let's say we have our inverter. This is from a transient simulation standpoint. We're gonna, on the first order, we're gonna pretend like we've got a resistance to ground, or effective N, and a switch. And then we'll have a switch for the P. And this will be R effective P. Okay, so that's kind of what the resistances look like. Now, remember to get when we said we wanted to have a 50%, so if you want a V in, V out, and you wanted this transfer function to be at VDD over 2, we said we wanted to make the beta of n is equal to beta of P, okay? If we want the rise fall time or prop delay rising and falling to be the same, we need to do the same thing for R effective N and R. So for prop delays, and fall times to be the same, we want R effective P to equal to R effective N. Okay, so what that means is if you're, let's say, if I have my NMOS and W, so L is 180 nanometer, my W is 1 micron. This is for first order, by first order approximation, okay? I wanna make my PMOS So L is again 180 nanometers. I want to make that width be, so this is our effective 2.7 kilo ohms, right? Now, what width do I need to make this 2.7 kilo ohms? I need to make it the width, let's see. Um, 6.5. So I want to make this width 6.51 kilo ohm over 2.7 kilo ohm times 1 micron. Okay, so it's 6.5. So I want to make this width 2.4 micron. I'm probably getting too fast for you guys, but does this make sense? That I want to make the width, I always end up making the width of, almost always end up making the width of my PMOS wider than the width of the NMOS for two reasons. One is to try to distribute my noise margin the nicest around, get my noise margin low and noise margin high to be the same. But also if I want to have my rise fall times and propagation delays to be similar, I'm also making the width of my PMOS larger than the width of my NMOS. And it's almost a lot of times it seems by a factor of 2 to 3. Okay. Everybody good with this? Any questions? Okay, so wait, was there a question? No. Okay, so we're gonna assume, okay, so that's there, okay. Now, because we're talking about prop delay, remember, or delays generally, we had, there's this capacitive. So we have current or resistance, and then we have capacitance. So we have the load capacitance, but each one of these transistors has a capacitance that's a parasitic capacitance itself. Remember that. So this is the resistance. But remember that if we draw the cross section for the device, so this is the silicon dioxide. So we have a bunch of capacitances here. So this is an NMOS, gate, source, drain. So we have the capacitance of these guys. Okay, so the drain to substrate capacitance and the source to substrate capacitance. And then we have the gate to channel capacitance, right? So we have gate capacitance, we call C sub G, and then we have C drain and C source. Okay, so we got to add those to our model. Okay, so again, the length you're going to assume for the devices are going to be 180 nanometers, and you're going to assume that, so if I look at this from the top, so this is a side view. If I look at it from the top, it's going to look like, so I have a gate, and then I have my active. Okay, and then I'm going to have my active contacts. I'm drawing this really badly, but now remember that, so this is my length, and this is always, I'm going to keep it constant, but I'm gonna, to get my resistances, you know, whatever I want, this width is gonna change. Width is a variable. So my capacitances are gonna also change as a function of width, right? If I make the width longer, my gate capacitance is this. So if this gets bigger, I'm gonna have a bigger gate capacitance, and my drain source is like this. So if I make the width longer, my my source and drain are gonna increase in size as well. So we can also have an equivalent. We can have a equivalent gate and C sub G and an equivalent C sub D, C sub S. And the book, whoops, why did I just do that? Nope, sorry guys. Why did I close the book? Huh? Oh, okay. So we have also helpfully got an equivalent gate capacitance value. So again, for our TSMC 180 nanometer process, this is this equivalent C sub G. And notice it's given in femtofarads per micron of width. Okay, this is like really important to remember. This is assuming the length is a minimum length of 180 nanometers, but this capacitance, as you increase the width, goes up by, we gotta multiply the width by this guy. So C sub G ends up being 1.67 femtofarads per micron. Okay, and C sub G is the same for the N and the PMOS, because if you guys remember, the gate gets created at the same time. Now, C sub D, the drain and the source capacitances, which they're both called C sub D, because again, remember that the drain and source are symmetric. Those are going to be different for the PMOS and the NMOS. Okay, so this is for the C sub D for the N. Again, it's given per femtofarads per micron. It's 1.12 per micron. And for the P, it's 1.24. I mean, to me, they're almost the same. I mean, that's not really gonna, within the accuracies of all these hand calculations and stuff, it's really about the same, 1.2, 1.1. But the C sub G is a little bit higher, 1.67. Okay. So, and you can also calculate this, as we'll see, or get it from simulations. So where are we? So basically what happens is, let's see, what were those values? C sub gate was 1.67 femtofarads per micron. And so in the case of our 1 micron NMOS, C sub gate would be 1.67. Gate effective would be 1.67 femtofarads per micron times 1 micron, so is equal to 1.67 femtofarads. Then in case of a 10 micron NMOS, C sub gate effective would be 1.67 femtofarads per micron times 10 micron, so is equal to 16.7 femtofarads. And C sub drain and C sub source does the same accordingly, okay? But that one's will be different for NMOS and PMOS. Okay, so in aggregate, what we'll end up with is, whoops, I wanted to add it here. So we had, first we had the resistors only, and now we're going to add the capacitances to it. Okay, so we're going to have I guess I should probably really just draw it one at a time. Sorry, guys. Let's see. So I'm going to add this. Resize. So if I was just going to look at the N, so just NMOS. So it would have this guy. Okay, it has a certain drain capacitance, a sort capacitance, certain gate capacitance, and it has a certain IDSN depending on the voltages. But my model is going to be, my simplified model that I'm claiming is pretty good, has an effective resistance and it has a effective drain resistance and effective source resistance, capacitance. I'm sorry, effective. Okay, and then I'm going to draw it like this. It has a effective C sub n effective gate capacitance. Okay, and the PMOS is going to be similar, except, you know, it's going to have its own effects. So here's the NMOS model. So you have this R resistance. So this R is like our R sub n. Okay, so this R is our R sub n. As this K value is how much bigger you are than your minimum size device, than what this was calculated for. That means if I'm using the R sub n value for a 1 micron transistor, my K, if I have a 10 micron wide device, my K would be 10. So my resistance would go down by a factor of 10 as my transistor gets wider. And this is what ends up being fairly confusing. Does that make sense, guys? Everybody okay with that? So this R is R sub n, and this K is how much bigger this particular transistor that I'm trying to calculate is bigger than my minimum size transistor. And the capacitances are the reverse. The wider this device is, the resistance goes down by a factor of K, linearly with a factor of K with my width, but my capacitances go up linearly with the width, okay? And in addition here, we're gonna make another simplifying addition is that C sub gate is equal to source, the effective C sub G is equal to C sub S is equal to C sub drain. Okay, that means, you know, 1.67 is approximately equal to 1.12, 1.12, all femtofarads. You guys hear my voice dropping as I'm making cheesier and cheesier assumptions here, but anyway, this is all first order assumptions for hand calculations. Okay, and so then yet another simplification is we're going to assume for the purposes of these lectures that we're going to do is that the effective resistance of PMOS is equal to 2 times the effective resistance of the NMOS. Remember that in actuality, actuality in our 180 nanometer process, that ratio is more like, or effective P is more like 2.5 times the R effective N. But we're gonna go with this assumption at the moment, okay? Doing all our baseline calculations this way, okay? So basically, you need to make, if you have a 10 micron wide PMOS, it's still gonna have twice as much resistance as a 10 micron wide NMOS. But its capacitance is only gonna be the same as a 10 micron wide NMOS, okay? But the resistance is gonna be double, okay, for the same width. Everybody with me? Horribly confused? No response? Okay, let's do this. Okay, let's take a look at what this looks like, okay? Of course, the answer is given here. Okay, so we'll do this, and then I promise you guys are off the hook for the time being, for about a week. Okay, so this is what this looks like. Okay, so I'm gonna start drawing these one at a time. Okay, over here, I've got my, so this number 1 means that this is the same width as a unit NMOS. This is the same width as twice a unit N or PMOS. Okay, so this is gonna be R. So this is the NMOS. So I'm gonna just call it R. So it's this R here. So R. Let's see, we had our switch. This is the capacitance of the drain of this guy. Okay, this is the capacitance of the source. Okay, and this is gonna be the capacitance of the gate. Okay, it's all times 1 because, you know, in this case, K is equal to 1. Okay, so this was our NMOS. Okay, there's this guy. So now I'm gonna draw this guy. Okay, this guy is R is 2R over 2. So the base is 2R, the base resistance is 2R, but it's twice as wide. So it's 2R over 2. So it ends up being R. Now its capacitance ends up being 2C because K is equal to 2. Okay, so I have twice as much capacitance because remember we made this twice as wide as the NMOS. So it makes sense that its drain capacitance is twice as much. Okay, and by the way, a capacitor, it doesn't matter if this goes to supply or ground. As long as it goes to a DC value, makes this in parallel with that. So they can just add. It doesn't matter. As long as they go to a DC, their other end goes to a DC value. Okay, so that'll come in handy a little bit. Okay, and then I have the C source, 2 C's. The source capacitance is also twice as much. Okay, then I got VDD here, and then the gate is also 2C. And the gates are connected. Okay. And note that the drains are connected too. So I got to connect the drains and it goes out. Okay. Now I've got the same thing on sitting on the output. So I'm going to try to cut and paste this. Okay. Oh. Okay, it almost worked. Okay, so this is what I end up with as this model. Okay, now I want to figure out the delay. Okay, this is fan out of one inverter. So what it's asking me is it wants to know the delay from here to here, from A to Y. Okay, and notice, so it doesn't, all this stuff, in this case, all this stuff doesn't really matter because I'm just, this is figuring out what happens out here. Okay, what here? I don't really care about that in this question. I want to just a delay from A to Y. So from A to this point. So I can basically ignore all this stuff in my little calculation here. Okay, I can just get rid of all this stuff. Okay, and just worry about this. Okay, does that make sense, guys? Any questions about that? So I'm gonna do something that'll be hard to recover from. I'm just gonna do this. Okay, I don't care about that stuff when I'm calculating just this delay. Okay, now, and also remember that I'm assuming that A is being driven by a, you know, good voltage source with a perfect rise time. So that means I can also pretty much ignore these guys because there's a, you know, whatever's driving this doesn't have a resistance. So I need to calculate this to figure out the delay of this stage. Okay, so let's look at, let's say, the fall time. Okay, the fall time, this switch closes and this switch is open. So if this switch is closed, let me close that. Okay, what I'll get as the resistance is R. Okay, and now let's look at the capacitances I get. Okay, sorry, I didn't draw this. Okay, so this capacitance doesn't matter because its top and bottom are both grounded. So this is really out of the picture because top and bottom are in the same voltage. It's not going to affect the delay. And I said that because this is hooked up to a constant bias, this is hooked up to a constant bias, I could just add these two in parallel. So that's 3C. Okay. And then I have just realized I'm going to end up with too much delay. I did something. What did I do wrong here? So this is 2C. This is C. This is 2C and this is C. So I'm going to end up with, oh, sorry, these are all add up in parallel. What am I saying? So R times, sorry guys, I confused myself for a second. So 3C for these guys. Okay. Plus they're also in parallel with these capacitances here. So plus 3C. So the delay is equal to 6RC, okay, which is what I get here. So basically it's the delay of this, essentially it's the delay of this resistor discharging these capacitances. So it's the RC delay of discharging this guy. And I can do the same thing for when I'm pulling up. when this guy shorts, when I'm pulling up, I can basically have this R here. I have these capacitances, and that pulling up is also ends up being 6 RC. So that's an example of how we would use this thing. Okay, so I'm going to stop right there, guys. And but this is sort of the approach towards this simplified delay calculation. Any questions?
Yeah. So the capacitors are in parallel because we have the VDD connected to one and ground connected to another on the NMOS and PMOS, right?
That's correct. Yeah.
Typically, the PMOS would be connected to the PMOS capacitors would be connected to VDD, and then the NMOS would be connected to ground. Or does it really matter?
That's pretty typical because you got to remember that typically the N MOSFETs are sitting like N plus. Their substrate is grounded. So all these capacitors are connected to ground. And a PMOS is sitting in an N well. This is the P plus, N plus. And so that's connected to VDD. And so these guys are also connected to VDD. So almost always, I shouldn't even say almost, always essentially, the NMOS capacitors get connected to ground on the other side, and the PMOS capacitors get connected to VDD. It's not almost always, yeah.
And then we just focus on like the middle part for this specific circuit itself, right?
Yeah, so you always have to think about what you're getting asked to calculate. So this is the delay from A to Y for this guy. So that's why we sort of ignored this part. And A, we're being driven with a voltage source, so we can kind of ignore the gate as well. So we just worry about the middle part, yeah.
And then we ignore like the top, like VDD2C and the bottom C.
Yeah, exactly. Because also note that this capacitor also both top and bottom are connected to the same DC voltage. So it doesn't matter, you know, it's not adding to any delay or any transitions. It's not changing at all. Same with this guy. It's top and bottom are connected to ground. So there's no charging or discharging of this guy or this guy. So we can ignore both of them.
Oh, because they're separated by the switch, right?
Yeah.
Gotcha.
Yeah.
Okay.
Any other questions, guys? Okay. Yeah, go ahead.
I had a quick question. So NMOS is normally tied to VDD. On SPICE programs, why is it not set by default? Like, why is it not connected by default? Is there like a reasoning?
Yeah, you know, there's two models. So you'll see. Well, I'll tell you the reasoning. Is because when you're doing analog design, you can do all sorts of crazy stuff and connect stuff to all sorts of crazy biases, etc. It's just you don't really tend to do any of that stuff in digital design because they are like really dangerous techniques unless you're paying a lot of attention. So you know, you can change things around the substrates, etc. For example, like in some processes, a lot of processes have so-called deep N wells, which you can even separate the NMOS substrates, but it's just stuff you do not do in digital design. Because digital design, what you're trying to do is you're trying to simplify everything so you can think of everything in terms of like gates. You don't want to be thinking about the specifics of how am I tuning some transistor and some gate. If you do that kind of design approach, when you're going to lots and lots of transistors in your design, some bad's going to happen. You're going to forget to keep track of some exception you made. But in analog design, you're sort of hand tuning, not quite, but almost hand tuning every single transistor's performance, and you're hand tuning them for some funky behavior. And you have to keep track of all those variations. So anyway, long story short, all that stuff is for analog design, so that you can do the crazy stuff that analog designers do.
Okay, thank you. That makes sense.
Sure.
Wait, actually, go ahead.
Go ahead. Sorry.
So to follow up, so in digital design software, would it be abstracted away, like that level of control?
Yeah. So a lot of times, what you see in in digital design is, even in SPICE, there is 4 terminal models for NMOS and PMOS where you shows the substrate connection. And then you'll see 3 terminal models. So even if you go to PMOS, I don't know if you're using LT SPICE or you're using PSPICE, you'll probably in your library have a 3 terminal model for NMOS and a 3 terminal model for PMOS, where they've assumed away the substrate to be sort of connected to VDD or whatever. And same with like logic gates. If the logic delay gates are already, assuming you're connected, everything's connected up to VDD or ground.
Okay,
so they are abstracted away. Yeah.
Okay, thank you.
Sure. Okay, guys, just one more announcement. Sorry, I forgot to do that. So because we're having the test on the Tuesday before we come back, I'm gonna have, I'll still have office hours during the, so obviously I'm gonna have the office hours tomorrow, but I'm also gonna have office hours the Friday during the break. So, just in case, you guys have got some last minute questions or whatever. And I think I'm gonna also probably, I'm gonna have to see my schedule, but I'll probably also put in an office hour on Monday after the break to make sure that you guys get any last minute questions answered. So I'll pull that as part of the announcements. Okay, guys, have a good break.
All right, thank you. You too.
Thanks. Take care.
If I start your question, do we
Yeah,
have
sure.
a class on Tuesday? So like after break, are you just gonna like post the test?
Yeah, I'm just gonna post the test and you guys just crank on it. So we're not gonna have a class. So I think I'm not sure if I posted right at the class, and you guys will get 24 hours, return it at whatever it is, 7 p.m. on Wednesday, or I think somebody was asking if I could post it earlier, and then make that the 24 hours, but I'll decide on that. But the Tuesday we won't have a class. So just guys focus on the midterm.
Got it.
Okay. Okay, guys. Take care. Have a good break. Bye.
Bye.
Have a good one, Professor.
Take care.